So in this video and the next couple, I'm going to attempt to help review and simplify the concepts here that we find in objectives 4 through 8 in Unit 10. Now, in Unit 10, objectives 4 through 8, they all deal with finding extreme values, finding when you have a local max, an absolute max, local min, absolute min, and where those occur. So we talked about the key concepts being that let's say here we have this function f of x on a closed interval, and we see we have a local max right here, and that's where we can't find local maxes anywhere unless the f prime equals 0, or in this case the f prime does not exist. So when f prime equals 0, or when f prime does not exist, that's what we call critical points. So these are the only places ever where we're going to find a local max or a local min. So critical points, f prime equals 0 or f prime does not exist. So when you're looking at a function, you're given a function, you're asked to find where do we have a local max? Well, the first thing you have to do is find the derivative, set it equal to 0, and then find where the derivative doesn't exist. And those are the two places where we're going to have possible, as I say, extreme values. But we also might find extreme values at endpoints. So endpoints of an interval, we'll always have an extreme value at an endpoint. So endpoints are just the endpoints of the interval. So let's see, how can I make this look good here? Critical points and endpoints, A or B, I guess. So f of x on the interval from A to B has extrema if and only if, only when, let's see, only when, now okay, so that's good. So f of x, this is the key concept. F of x on the interval, closed interval from A to B, has extrema only when, like I said, only at critical points and endpoints. And that doesn't mean we will always have an extreme value if f prime equals 0. It doesn't always mean that. So here's an example. Let's say we have f of x, and let's say f of x looks like this. Kind of like that. All right, so we have a closed interval. Now, the extreme value theorem guarantees that we will have an extreme value somewhere. We will have an absolute max and we'll have an absolute min somewhere on that closed interval. We have to. We have to have an absolute max and an absolute min on an interval if it's closed. The function is continuous on a closed interval. We're going to have a max and we're going to have a min. But it doesn't mean we're going to have it where f prime equals 0. Because here we have a closed interval. Here we have f prime equals 0, and this is no max, no min. No max, no min. Because for you to have a relative max or min, you're going to have it has to be the highest or the lowest point of all the ones right around it in this small neighborhood. Well, we don't have that here. But we do have an absolute min here, but the absolute min happens to be at the beginning of the interval, and the absolute max happens to be at the end of the interval. So sometimes we don't have a max or a min where the derivative is equal to 0. And sometimes the derivative, there's nowhere in the closed interval in which the derivative doesn't exist. So sometimes you can find where a derivative doesn't exist, sometimes you can't. Maybe take, for example, y equals absolute value of x. So if we take absolute value of x on the interval, let's say from -1 to 2, well, we can draw the graph. We know what it looks like, but if you did the work, if you did it algebraically, you would find the derivative. You would find the derivative doesn't exist at x equals 0. You'd find that at f prime of 0 does not exist, but you'd find also that we have an absolute min at 0, 0. And you'd find an absolute max right here at 2, 2, and you'd find a local max right here at the point -1, 1. And so what would that look like? Well, if you did it analytically or using some algebra here, you'd find, oh, f prime test. You'd use your f prime test. You'd find where f prime doesn't exist at 0, endpoint -1 and 2. You would find that f prime is negative on that interval, so f is decreasing, and you'd find where f prime is positive on that interval, so f is increasing on that interval. And when f prime, I should say, when f prime changes from negative to positive, we have a min. If it's the only place, if f prime is always negative from the beginning of the interval to from the beginning of the domain to this only critical point, and then it's f prime is positive from this only critical point to the end of the domain, then we would say we have an absolute min. And so if f prime changes from negative to positive, we automatically have a local min. And there's ways to test the y values to see if you have an absolute min. If you have more than one min, the lowest min is the absolute min. It's on a closed interval, and on and on. So that's the concept. And then we talk about inflection points, and we talk about the second derivative test. But we'll get into that in the next video. So that's the first part, right? That's the first part. That's probably objectives 4 and 5, something like that, where you find critical points and endpoints, and you test them, and you could find maxes, mins, and things like that. So always, 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 you find, let's do one more thing here. If f, and you have f prime, so this is the first part of the objectives 4 through 8. If f is, let's go with f prime. If f prime is positive, that means that f is increasing. If f prime is negative, that means that f is decreasing. Period. That's it. Know that, and then when we get to the next video, we'll start talking about, well, how does f double prime fit into that?